16th, we will cover as much as we can. Okay, if we can cover only 2 years, then we will just push back one of the year to Saturday. Okay, Saturday basically we will review exam paper, the past 3 years exam paper, and only for the questions that are relevant to CA2. Alright, and if there is any leftover from Friday, we will bring forwards, okay, to Saturday. So Saturday, if we cannot finish within 2 hours, we might extend to 2.5 hours. Let's see how does it go. Alright, a bit late lunch, never mind. Okay, then next week, of course, next Tuesday will be CA2. Okay, 2:30. Okay, at E8. Please be there early. Alright, please be there at least 10-15 minutes early. Get a seat. Okay, at CA2. And CA2 covers only chapter 4, 5, 6, 7, namely propagation in lossless media, propagation in lossy media, transmission and reflections, as well as transmission line. Alright, chapter 8, which is mischarge and signal stop section, will be excluded from CA2 as well as the exams, okay, due to lack of time. We don't have much time, I think, so everybody agree, all teachers agree that we don't have time to cover chapter 8, alright, so we will leave it up. Alright, although chapter 8 mischarge is quite important too, if you are going into circuit design, microwave circuit design, it will be a very important tool, and I advise that, if you are interested, read it up, okay, and if you have any issues, check with me, alright? Okay? Alright, transmission line. We have said that transmission line equations basically is the same as the, this computer is so slow. Okay, basically it's the same as the propagations in free space. Okay, we have the del squared E plus K squared, E equal to 0, and same thing here, we have del squared V minus gamma squared, B equal to 0. Therefore, gamma is equal to JK, okay, and it is equal to alpha plus J beta. So everything is the same, alright? This one, we have K is equal to beta minus J alpha, and this one we have gamma, which is equal to E minus JKZ. Let's say this gamma is equal to alpha plus J beta, and E minus gamma Z. So gamma basically is equal to JK. Alright, so this is what we have. Okay, and K is equal to omega square root of mu epsilon. Okay, epsilon can be equal to epsilon naught, epsilon R can be equal to epsilon C. Alright, so it can be either one of this depending on whether it's lossless medium or a lossy medium. Okay, but gamma, which is equal to square root of R plus AL times G plus JC. Alright, and we said wave propagations, we also have a zeta, which is equal to square root of mu epsilon. Alright, then what we see, what do we have here for Z? Z, on the other hand here, is equal to R plus J times omega L, omega C, so we have very similar characteristics. Okay, so same thing we have inside the transmission line. We have a forward propagating voltage wave, backward propagating voltage wave, forward propagating current wave, backward propagating current wave. The same as E wave and H wave in the free space propagations. So you can see that there really, plane wave is actually a kind of a transmission line as well. Now you can see down we have our Z. Okay, Z equal to R plus J omega L, J equal to over G plus J omega C. Alright, so this is once again. Alright, so this is the equations that you need to know. Z naught, okay, which is the characteristic impedance of the transmission line. is equal to R plus J omega L over G plus J omega C, and gamma equal to alpha plus J beta is equal to this one. Okay, these are the two equations that you will need to know. Alright. Now, for lossless line, okay, when I equal to G equal to 0, okay, when lossless line, I equal to G is equal to 0, alright, then Z0 lossless line, Z0 is equal to only square root of L over C. Because if I equal to 0, G equal to 0, and then J omega cancel off, is equal to L over C. Okay? Now, at this point here, I have questions to ask you. I equal to 0, G equal to 0. I is resistant. G is conductor. Resistance equal to 1 over conductor. So I equal to 0, G equal to infinity. G equal to 0, I equal to infinity. How do they get to become 0, 0 and 0 at the same time? Under what conditions they all can be 0 at the same time? Now, because you were not paying attention to the initially how the circuit model is defined for the transmission line. R is the resistance of the cable. Okay, resistance of the cable, that means it is this one. R is equal to rho L over A, which is the resistance over the cable which current flow. Okay, if it's coaxial cable, then it is the inner cable and the outer cable. Okay, this is the resistance. Now what is G? Do you remember this slide? This slide is your previous chapter 2 slide. We find the resistance. This resistance is what resistance? This resistance is the leakage resistance between the inner and outer conductor. So this is G. Now our G is a leakage conductor. So the two are different. The resistance of the current flowing in the conductor and the resistance of conductor to the current, leakage current are different things, right? They can be 0 at the same time. So do not think that, I equal to 0, G equal to infinity. No. Okay, we are talking about two different things. Alright? Where the heck is it? It's got this problem. Okay, so they are two different things. So I equal to 0 and G equal to 0 at the same time. Now, then the second question I want to ask you is that, okay, Z not equal to square root of Lg, then it is lossless, right? This is impedance. This is characteristic impedance. People don't associate characteristic impedance in anything, right? E over H, or in space, I don't care, I don't know what it is. But now, this is an impedance. And impedance is a real thing. And it is real. Right? I thought Ohm's law said if I have a real impedance, it's a resistance, and if the resistance is a lossy. How come I have a real impedance and now I'm saying it's a losses? Once again, okay, you have to pay attention to how the model is built. Alright, Ohm's law says that if resistance is real, then this is lossless. It's like this. This is current I, this is V. Alright, so if you measure the voltage across the impedance, and with the current flowing through the impedance, there is Ohm's law. So when it is real, it is lossless. But if you look at the model, the voltage and the current are not measuring at the same point. The current is flowing this way, the voltage is that way. Remember the transmission line like this? The voltage is measuring like this, the current is like this. This is not Ohm's law. Unless my voltage is measuring like this, then it is Ohm's law. V and I, V measured across, I propagate. But this is not. So this is not Ohm's law. Okay, so from this, that Ohm's law is not necessary, not necessarily hold, because it is, you cannot say apple and orange look the same. They are not the same. Alright, so the voltage they will define and the current they will define, they are not in the same directions. Okay, not in the same direction. So it's okay. Now, alright. So now, another similarity, okay, the wavelength and the velocity of propagations. Look at this velocity of propagation, which is exactly the same as here. This is V equal to C over square root of epsilon R. This one is exactly the same, V equal to C over square root of epsilon R. This is exactly the same. Alright? And if that is exactly the same already, what other things can be the same? V equal to F lambda. V equal to F lambda. Okay, so the wavelength will follow the same thing as well. The wavelength will follow the same thing there. Lambda will be equal to lambda naught over square root of epsilon R. Okay, lambda will equal to lambda naught over square root of epsilon R. Okay, or you may want to prove to yourself that, okay, these equations here, okay, can actually reduce to these equations. Okay, go there and prove to yourself. Alright, this is for information for me. This is what called spatial domain, temporal domains, time domain, and distance domain. Now, next thing we want to do is to look at terminated transmission line. Now, just what we have said so far is transmission line without termination, the infinite transmission line, or a plane wave propagating in free space without boundary. Okay, so our plane wave hit a boundary, zeta 1, zeta 2, it's the same thing that our transmission line hits a load. Alright, a plane wave propagate, hit the boundary, there will be refractions, there will be transmission. So same thing now, the transmission line hit the boundary, there will be refractions, there will be transmissions. So everything's the same. You can see that even notation is the same, that, when at a refraction, transmission and reflection, we set this point at z equal to 0. So this is minus z, positive z. It's the same thing, this is z equal to 0. So this one here, the length is z equal to minus d. It's the same thing. So we use z prime equal to 0 here, and z prime equal to d here is the same. They use L. Okay, so it's exactly the same. You can see that the way that they formulate the whole thing is the same. Alright, now the load is ZL. Okay, the load is ZL. So VL over IL is equal to ZL. Load is equal to ZL. Now, this VL is here, this IL is here. So this load now is the real Ohm's load. The Ohm's law load. Okay, the Ohm's law load, which is Z equal to V over I. And they are measuring according to Ohm's law. So this one, your ZL here, this one is the real load. Okay, it's not characteristic impedance. It's a real impedance. Alright. Now, I do not want to go through all these derivations. Okay, I do not want to go through these derivations. Okay, maybe I just mentioned, okay, all these derivations, you no need to go through, alright? There's no need for you to know how to do the derivation. All you need is actually how to apply the equations, okay? Now, basically, what is being done here is that, okay, the voltage, total voltage is equal to the forward propagating voltage wave plus the reverse propagating voltage wave. The total current is equal to the forward current wave plus reverse current wave. You can see that it's the same. Forward wave is E minus jk, backward wave is E plus jk. Alright, now because basically we are using lossless line now, so now we revert back to k. Right? How can I mix up the k? Okay, so we reverse back to the k notations now. Okay, E minus jk notation. We reverse back to k notations now. So when at L equal to minus z, okay, so we put the L back. This is the L to the minus z is at this starting point. Okay, it's at the starting point. It's down here. L equal to what D is here. Okay, L equal to D is here. Alright? Okay, so you put the L is equal to minus z inside here. So now you substitute L equal to minus z, you replace these two equations, become this equation. Now, the position at the load is L equal to 0. The positions at the load is L equal to 0 over here. Alright, so you substitute L equal to 0 here, you get V0 plus V0 minus equal to VL, and V0 plus over Z0 minus V0 minus over Z0 equal to IL. Alright, so this is the voltage at the load, this is current at the load. And according to Ohm's law, VL over IL is equal to ZL. Now, then you solve these two equations. You solve these two equations for V0 plus and V0 minus. Okay, you solve the two equations for V0 plus and V0 minus. This is what you get for V0 plus and V0 minus. And you sub V0 plus and V0 minus into these two equations again. You sub V0 plus and V0 minus into these two equations again. And I0 plus and I0 minus into the equations again. Alright, then you end up with these equations, and this is cosine, this is sine, okay, and then you change them to cosine and sine. Finally, you end up with these two equations. Now, what it means is that once you know the voltage and current as well as the load impedance, you can know the voltage and current at any point along the transmission line. Okay, once again, if this is a load here, ZL here, if I know IL, I know VL, I know ZL, three of them, since they are related by Ohm's law, I only need to know two, alright? I only either need, I don't know, either IL and ZL, or ZL and VL, or IL or VL, they are all related. Now, once I know that, I can know the voltage and current at any point along the transmission line. Okay, so the voltage and current along the transmission line we know. Okay, this equation and this equation you must know as well. We'll summarize it later on for you. Alright, and VL over IL is the impedance measured at this point. Is the impedance measured at this point. VL over IL is the measurement is the impedance measured at that point, and this is the famous transmission line equations. And this one you will need to know as well. This is a transmission line equation. Impedance measured at different points along the transmission line. Now, we will explore, okay, what is the significance of these particular equations later on, okay, by looking at the various examples. Now, then at the end of the transmission line, we can also find a reflection coefficient. Okay, the reflection coefficient, which is equal to V0 plus over V0. Okay, and this is equal to ZL minus Z0 over ZL plus Z0. So you see that now this gamma is equal to zeta 2 minus zeta 1 over zeta 2 plus zeta 1. And now this gamma is equal to ZL minus Z0 over ZL plus Z0. Once again, look at the similarity. The only things that you do not have in the plane wave propagation is this one. Because normally people will not measure impedance in a wave propagation. How to measure impedance along every point, right? Impossible. But transmission line can. Okay, so this is an extra that you do not have over there. Okay, Z at the point L equal to Z0 ZL plus J Z0 tangent KL Z0 plus J ZL tangent KL. Alright, so you have the extra equations. This is the extra equations that you do not have in the wave propagation. The rest are basically the same. Now, you also have the reflection coefficients at any point along the transmission line. Reflection coefficient at any point along the transmission line. Gamma L, this gamma L is at the load. Okay. Now, the gamma L at any point along the transmission line is gamma LE minus J2KL. Now, this is the part, remember this is the part where in the transmission and reflection we say that there are two vectors, the two vectors rotate and so on and so forth. This is once again come out here again. Alright. This is implicit, okay, inside here, but this is not expressively come out. Alright, so it is now come out in transmission line. So the refraction coefficient measured along the transmission line at any point, it is the same, that has the same magnitude of the refraction coefficient at a load, but keep changing phase. And the phase change is twice as fast. The phase change is twice as fast. Alright. And this gamma L, okay, although this is not special here, but never mind, we just block it off. Gamma at the distance L is equal to gamma L E minus 2JKL, which is equal to ZL minus Z0 over ZL plus Z. Okay, these are not special, but we'll block it out also. Okay, now once again, these two equations, these are the equations that you need to know. Alright, now, okay, so how do we normally analyze the transmission line problem? Okay, let's say I have a transmission line now with a load here, ZL, and the transmission line is supplied by a source and a source impedance. Okay, so how do we normally analyze this kind of issues here? How to analyze this kind of circuit? Okay, what we do normally is we know ZL, right? ZL has to be given, because if you don't give ZL, how do I know what am I going to analyze? So once I know ZL, I will find the impedance at this point. Cos Z in or it is equal to Z length L. Okay, I will find the input impedance at this point. And then this whole circuit will be replaced by a simple Thevenin circuit. My source is here, my source impedance is here, and my input impedance here is here. And this simple Thevenin circuit is very easy to analyze. I can, because if I have to know the VG, I know the ZG, so I can know the VI and know the ZI. Right? the simple Thevenin circuit can be analyzed very quickly. Alright. Now, we will see once again, okay, how this thing is going to, in example, how we, analyze these particular Thevenin circuits with by using a few examples. Alright, but at this point of time, okay, at this point of time, we want to emphasize again, once again, that the voltage at any point is related to the current at the load and the load itself. Current at any point is related to the current at the load and the load itself. Alright, now, we can also, from the equations here, okay, from the equations here, these two equations here, we can also use this VI and II. Okay, VI and II are actually determined from the Thevenin equations. Okay, we can also use the VI and II to calculate the VL and IL back if we want to. Right? If we substitute VI here, ZL we know, Z0 we know, KD we know, KV we know, we can find the current and we can find the voltage back the load again. So the whole transmission line equation solutions will become forward, move ZL to forward to become a Thevenin equivalent circuit, and then move backward, and then move forward, to and flow and to and flow. Okay, we will see, look at some example later on. Now, the input reflection coefficient is okay. Okay, we look at some example here. A 100 ohm transmission line is connected to a load consisted of a 50 ohm resistor in series with a 10 picofarad capacitor. Find the reflection coefficient gamma L at the load for a 100 Hz signal, 100 megahertz signal. Now, reflection coefficients. Why do we need 100 megahertz? Oh, because we have a capacitor here. Okay, the impedance of a capacitor is dependence on omega, right? So my ZL here is equal to 50 plus 1 over j omega C. Okay, C is 10 picofarads here. Alright, so I need the frequency. So if I have my ZL, which is equal to 50 plus 1 over j 2 pi times 100 megahertz, I can find the reflection coefficient. Okay, so there you go. I equal to 50 ohm, C equal to 10 to the power minus 11 is 10 picofarad. Okay, Z0 is equal to 100 ohm, F equal to 100 megahertz. Then we can have ZL. And once we have ZL, the reflection coefficient is equal to ZL minus Z0 over ZL plus Z0. Alright, ZL minus Z0 over ZL plus Z0. Now, then the next thing is find the input impedance Zin at the input point end of the transmission line. Its length is 0.125 lambda. Now, this is the direct applications of this one. I know ZL, I know Z0, I know K, okay, and I know L. K actually I do not know at this point. K I do not know. Do I know K? K is equal to the epsilon r is not given. The velocity is not given. I do not know K. But luckily L is given by 0.125 lambda. Because K is equal to 2 pi over lambda. So KL, when L is expressed as 0.125 lambda, lambda cancel. Alright? Okay. Remember, this lambda here is not the free space wavelength. Okay, transmission line, the wavelength is never the free space wavelength. Okay, unless they tell you air coil, air field. Okay, if you see this expression air coil, air field, air whatever, then you can assume that the wavelength is the free space wavelength. Otherwise, you cannot. Alright, so you substitute inside here. Okay, you substitute inside here, and then you just do the derivation. Okay, so this is half of the application from this side to this side. Now, example 2, a lossless transmission line with Z0 equal to 50 ohm and D equal to 0.3 lambda connects a voltage source Vg to a terminal load of ZL equal to 100 ohm. It is known that Vg equal to 100 volt and Zg equal to 25 ohm. Find the current II and voltage Vi at the left terminal of the transmission line. Vi and II. What are the current ZL and VL at the load? What are the current and voltage at the middle of the transmission line? At the middle of the transmission line. Alright? Okay, once again, the important formula is always this one. The transmission line equation is always this one. Alright, so now you find the input impedance at the terminal there, which you sub in everything is equal to this particular value. Alright, and using the using the Thevenin equivalent, because now the whole circuit is replaced by Thevenin equivalent Vg, Zg, and Zin. Vg, Zg, and Zin. Alright, so II is equal to Vg over Zg plus Zi. II is equal to Vg over Zg plus Zi. This is Ohm's law. Okay, it is from here. And Vi is equal to II plus Zi is from there. Okay. Then we go back to the equations. Okay, we go back to the equation previously, in slide 26. Okay, we substitute Vi, we can find IL. Okay, and we can find IL. And of course, VL is equal to IL times ZL. Alright, VL times IL times ZL, so we find VL. Now, you see, what we do is, from ZL, we have the transmission line equations, bring forward to the input, and at the input, we use Thevenin to analyze the V and I, and then with V and I substitute back to the equations, so go back to the VL and IL, and then after that, we use the forward equations again to find the voltage and current at any point. And now they want V, L equal to D by 2, we substitute back L equal to D by 2, so we can find the voltage and current at any point, at this point here along the transmission line. Okay, so the procedure once again is that when you are given ZL, you use ZL to find a Zin using the transmission line equations. From the Zin, from a Thevenin circuit, you find the Vi and II. Vi and II, you go back to find VL and IL, and from VL and IL, you can find voltage and current along any point of the transmission line. Okay, so the process is quite standard also. Okay, then the next thing is very standard, is also standing wave. Since you have forward propagating wave, backward propagating wave, once again we have standing wave. Okay, we have forward, backward propagation, standing wave. Why everybody's so tired? Not much of a concept, all the things they have learned before. Hey, why is it so slow? Now, once again, okay, remember our two vectors. our two vectors. One and another vector which is gamma, okay, and it's rotating with a angle here. Okay, so when this is fixed, this length is 1, this length is gamma, and when gamma is rotating, that means when you change the value of Z or you change the value of L, okay, this one will be rotating like this, okay. It will describe the circle because gamma L, the gamma L magnitude is constant, so it describes a circle. So you can see that when the two are in line, in phase, it becomes a maximum. When the two are out of phase, it becomes a minimum. Alright, so the total, the sum is now like this. Maximum at this point, this is in between, and then when minimum at this point, and go and maximum at this point. So once again, okay, when the phase angle is equal to 0 or 2 pi is the maximum. When it's equal to 2n plus 1 pi, it is maximum, in minimum. Okay, so same thing here. Now we have these two sets. Now these two sets, what is the difference between these two sets? And this one. What is these two sets? Is this one. This one that you have learned previously in the plane wave refraction and counter transmission. The difference is that these two are actually special case of the slide that we see here. This one, the phase angle of gamma is either 0 or pi. Okay, because this zeta 2 is not a complex number. We assume that zeta 1 and zeta 2 are real. Zeta 1 and zeta 2 are real. Therefore, if zeta 1 and zeta 2 are real, therefore gamma is real. And gamma is real, therefore it is either is a positive or negative number. Okay, so the phase angle is either 0 or pi. But now our impedance ZL here can be complex. Okay, just now we saw an example in a resistance and capacitance. So when it can be complex here, that means gamma here will have a phase angle theta. Okay, we'll have a phase angle theta. There you go. Okay, you have a phase angle theta over here. Alright, so these two slides are the generalization. So in fact, okay, this slide and the next slide, so slow. Okay, so actually these equations here, okay, these two slides, this slide and the previous slide, the equation for Vmax and Vmin is the same as the transmissions and refractions, okay, for plane wave. Okay, so this equation is more general. So if you want, you can just include these two in this equation, and then when you have plane wave, you just put theta L either equal to 0 or pi. Okay, then you get from there. Alright, so this is a more general equations. And once again, alright, we still have standing wave ratio. Okay, we still have standing wave ratio, and we still have standing wave. So it's the same kind of thing, and it is the same kind of thing that when I equal to the maximum, okay, voltage when I equal to maximum, okay, voltage is equal to minimum. Alright, and so on and so forth. Vmax, Vmin, Imax, Imin. Alright, so it's the same kind of thing. And for special terminations, now it is the special termination is what happens if the load is a special load. Okay, when the load is a okay, when there's a match load, gamma L equal to 0. How to get gamma L equal to 0? Gamma L equal to 0 is when ZL equal to Z0. Alright, ZL equal to Z0 when you get gamma L is equal to 0. When you get gamma L equal to 0, standing wave ratio is equal to 1. And is there any standing wave? No standing wave. Okay, because that means when the wave come here, when it hit the load, since ZL is equal to Z0, all the power will be transferred to, there will be no reflections. Now, what is when gamma equal to -1? Gamma L is equal to -1 is the same as when you have here, when your propagation is when a wave hit at the perfect conductor. We have seen that special case in our previous lecture. When the wave hit the perfect conductor, gamma L is equal to -1. Okay, so S is equal to 0 and ZL is equal to 0 here, which is a short circuit. Okay, a short circuit inside in a transmission line is the same as when you hit the perfect conductor over here. Alright, now this case here we never discussed in the wave propagation is when gamma L equal to +1. Gamma L equal to +1 in this case here, zeta 2 must be equal to infinity. Right? We can't have zeta 2 equal to infinity in the wave propagations here, but we can. Okay, all we have to do is just do open circuit. Okay, open circuit, standing wave shear equal to infinity, and your gamma L equal to 1. Any questions so far? You see, I did not go through the detailed derivations. I just point out all the similarity, because the important thing here is the applications and not the derivations. Okay, the similarity, and we rather spend time looking at the applications. Now, the next things that we want to look at is power flow. Alright? In plane wave, we have pointing vector. Okay, down here we have power flow. Now, what is the difference? Remember, pointing vector is the power density flow. Okay, now this one is the actual power flow. Now, you can see from the units, pointing vector is equal to half real of E cross H conjugate. E is volt per meter, H is ampere per meter, so it is equal to watt per meter square. The unit is power density, and this power is half of real V cross I conjugate, and V is voltage, I is ampere, so this is watt. So this is power, this is power density. Okay, that is the difference between the two. But the equation is again similar. Half real VH conjugate. Alright. So now, just now we show you how to go to and fro to find the voltage and current. Okay, now we look at the power. Same thing, if you want to find the power, you get ZL here, translate into Z in here, using the transmission line equation. And from the Thevenin's equivalent circuit, you can find the power that go into the transmission line very easily, right? You know VI, you know ZI, you know II. So the power that go into the transmission line will be VI, II conjugate. Okay, will be equal to VI, II conjugate. Right. Then what is the power supplied by this load? Alright. The power supplied by the load will be equal to, following this equation, will be half of real VG II conjugate, right? Power is equal to half of real VI conjugate. So power input to the transmission line is half of real VI II conjugate. Power supplied by the source is equal to VG II conjugate. Power dissipated by the internal resistance, internal impedance is equal to the difference of these two voltage times II conjugate, right? The voltage across ZG. Alright, so you can see that there are all the things here. Powers across ZG is equal to half of VZG. Okay, half of VZG conjugate. Power input is equal to half of VIII conjugate. Alright, so you can find from the Thevenin equivalent, there are questions previously come out like this. Find the power supplied by the source, find the power dissipated by the source impedance, find the power input to the transmission line. Alright, so you can have various kind of things. And remember, from here, the similarity runs very deeply. Remember this one, we have it to as equal to half of E squared over zeta. Same thing here. This one we can have it at half of V squared over Z. Same thing. You see half of V squared over Z. Alright. Now the only difference is that in this one, because zeta is real, okay, so you can take the zeta out. This is real, right? So if zeta is real, you can take it out like this. But for this real, this Z can be complex. Okay, if Z is complex, once again you have to make sure that you know how to do this real part of complex number. Remember, we have mentioned it earlier on. We have mentioned earlier on is that real part of A plus JB is not equal to 1 over A. It is equal to real of A minus JB, A squared plus B squared, which is equal to real of A over, which is equal to A over A squared plus B squared. Alright, this is the real part. Or if you're using the cosine, okay, you can do that as well if you express it this way. But just remember, is that now because the Z is a complex number, you cannot take it out just easily like this. You have to do the real part of the complex number. Okay, so that is the difference. Okay, between this one and that one. But the rest are the same. Okay, power supplied by the source will be equal to power dissipated. Power supplied by the source will be equal to power dissipated by the source impedance plus the power input to the transmission line. Right? Power conservation. Now, if the transmission is lossless, then the power supplied by the then the power the input to the transmission line will be equal to power dissipated by the load. Because if transmission is lossless, that means it does not dissipate any power. Alright, once again, power supplied by the source will be equal to the power dissipated by the source impedance plus the power input to the transmission line. Alright, so this power is equal to this plus this. But power input to the transmission line, if the transmission is lossless, it will be equal to the power dissipated by the load, because the transmission line itself, being lossless, cannot dissipate any power. So you can have PS equal to PZG plus PI, and PI is equal to PL. Alright? Okay, let's look at the example again. It's again forward, backward. A lossless transmission line with Z0 equal to 50 ohm and D is equal to 1.5 meter connects the voltage source VG to a terminal load of ZL equal to 50 plus J50 ohm. If VG equal to 60 volt, operating frequency F equal to 100 megahertz and ZG equal to 50 ohm, find the distance of the first voltage maximum. What is the power delivered to the load PL? Assume the speed of the wave along the transmission line equal to the speed of light, c. Alright, so the velocity is c, wavelength is just lambda, okay, or lambda naught. Okay, the following information is given. Lambda is equal to 3 meter. Now, at this point here, you need lambda. Why? Because the length d is given as 1.5 meter. It's not given per wavelength. It is given by 1.5 lambda. Then you don't need this information. But because d is given as number, then you need the k is equal to 2 pi lambda. You will need the lambda. Alright, so Z0 is there, D is there, Vg, Zg, Zl, frequency, lambda. Refraction coefficient and the load, very simple. Zl minus Z0 over Zl plus Z0, 50 plus J, 50 minus 50, and so on. Alright, now, once you get the refraction coefficients, you change it into the magnitude and the phase. You need the phase angle, remember, you need the phase angle to sub into the equations. So you got the phase angle, and then you sub into the equations, and then you get the maximum. Okay, you get the maximum. So that one is easy. Now, the next one is that you have to find the input power. Okay, so you start with ZL. You find input impedance. Over here. Okay, you find input impedance Zi. Oh, also exactly equal to 50 plus J 50, which is very good. Okay, and then you can find II from the impedance. So QII is equal to Vg over Zg plus Zi. You find II. Right? Now, why you want to find II? This guy is smart here. Why you want to find II? Remember, power is either half V squared Z or equal to half I squared Z. Okay, if you rear of this and rear of this, now remember just now we said that rear of 1 over Z got issues. It's not equal to this one, it's equal to this one. But rear of Z is equal to A. Rear of A plus JB is just equal to A. Right now, the rear of the complex number A plus JB is just equal to A. So you see that this guy is just smart. He find II in order to find the power instead of finding VI, you find II. So you find II, and then the power goes to the load half I squared, rear of Zi. So this straight away. So sometimes you see there are a couple of equations that you can use. Try to find the one which is a simpler one. Now, when ZL equal to Z0, okay, when ZL equal to Z0, the refraction coefficients gamma L is equal to 0. And if you substitute ZL equal to Z0 here, okay, you can see that into the transmission equations here, you substitute ZL equal to Z0 here, you can see that it becomes like this. Numerator, denominator cancel out, so the input impedance is equal to Z0. Okay, input impedance equal to Z0, input impedance minus Z0, ZL plus Z0. Okay, this is 0. So the refraction coefficient here is equal to 0. The refraction coefficient here is also equal to 0. Alright, for any length, so there is no refraction coefficient. But does not means that, okay, it not necessarily means that the power transferred to here is equal to anything. It's maximum or minimum because it's all dependent on Zg. Alright, the power transfer is still depending on Zg. Okay, so be careful. Alright, so when ZL to the Z naught, when ZL to the Z naught, the transmission line like this, the voltage go in, current go in, impedance the same. Z naught everywhere the same. Now when it is shorted, when you have a short circuit, ZL equal to 0. Now look at this standing wave. Look at this standing wave here. It is exactly the same standing wave that you see when you're dealing with transmission and reflection, when you hit a perfect conductor. When you hit a perfect conductor, you get the same standing wave as per this one. The only difference is at that time that we did not plot this normalized impedance along. Okay, normalized input impedance along. Now, aircon. Never mind. You see, remember, okay, this input impedance is not the same as this zeta. Okay, this zeta is what? This zeta is equal to E plus over I plus. Okay, this is E plus over I plus. But this impedance, this input impedance is what? This impedance is equal to the total current, total voltage divided by total current. Two different things. So you can see that when the total current is equal to 0, when total voltage equal to 0, okay, the impedance goes to 0 because impedance is equal to V over I. Alright? Voltage equal to 0 divided by current is equal to 0. But when the voltage is here, as maximum, current is 0. V over I. V over 0 is infinite. So now the impedance, the input impedance is infinite. The input impedance is infinite when at this distance away. Now, what is the consequence of this thing? Some students do not understand that this issue. Half a wavelength away, the impedance becomes infinite. What does it mean? One of the very important consequences is that when you want to design a circuit, you want to ground. Sometimes you ground the meter, right? You want to ground something, right? You design a circuit and ground something, right? Sometimes you design systems. You want to ground the cabinet, right? You want to ground the box. You want to ground something, right? Ground means connect to ground. But what is the length of the connecting wire or bonding wire? You want to bond this cabinet to ground, or you want to design a circuit. You want to have I want to ground it. What is the length of ground wire, and what is your frequency of operation? Remember, the length is a wavelength. If your grounding or bonding wire is exactly equal to the quarter wavelength away, so you are not grounding. No matter how big is your wire, you can have a big thick strand of wire ground here. You expect it, your cabinet, okay. If this is the cabinet, you expect, okay, now ground like this. This is ground. You expect this one is ground. It is not ground, alright? Because the impedance at this point here is exactly infinite. So actually, it's the same as not doing anything. You might think that, okay, I'm grounding it. This is a good ground. I connect a very thick ground wire, so I'm grounding this cabinet. No, you don't get it. This is one of the very significant things that a lot of people do not understand. And the impedance, your grounding impedance can change with frequency. Okay, so this is the issue of transmission line. Now open circuit is about the same. Okay, open circuit is about the same. We just reverse the voltage and current maximum because at short circuit the voltage is 0. At short circuit, current is maximum. Alright, but when open circuit, the current is equal to 0, the voltage is maximum. That's only different. Alright, so the impedance just shifted. 4 transmission line. When L equal to lambda by 4, this is also a very significant result. L is equal to lambda by 4, okay, your input impedance is equal to Z0 squared over ZL, okay, which is also very significant. Why is it so significant? Because you can actually use this to convert capacitor to inductor, inductor to capacitor, because you see that Z in ZL is equal to Z0 squared, right? So it's a constant. So if this is a capacitor, it can become inductor. These two are inversely proportional. Okay, and another way is that, like for instance, okay, I have this impedance, let's say 50 ohm, this transmission line 50 ohm. Now I have a load which is equal to 8 ohm. If I connect this one directly, there will be a reflection coefficient 8 minus 50 over 8 plus 50, right? So how am I going to make sure that there is no reflections? I can connect another transmission line. Length is equal to lambda by 4. Connect. And if the transmission line, let's say if it's Z prime, then my input impedance here will be equal to Z in will be equal to Z prime squared divided by 8. Right? Correct or not? According to that formula here, my Z in is equal to characteristic impedance squared divided by ZL. Right? Is it okay? Okay, so if I want this place to be equal to 50, I want it to be matched, I put this equal to 50. So my Z prime squared is equal to 400. Z prime is equal to square root of 400 equal to 20. So that means if I want to connect a 8 ohm load to a 50 ohm transmission line, and I do not want any refractions along this transmission line, what am I going to do? I just put another transmission line of 20 ohm, lambda by 4, and I kill all the refractions. Because if this is 8, this is 20, so my Z in here will be equal to 20 squared divided by 8 equal to 400 divided by 8 equal to 50. So I get 50 and then 50, no reflection. But you may want to ask, hey, how can you do that? Where are you going to find the 20 ohm transmission line? If you use physical transmission line like this, it is not easy because this one might not be 8. What happens if this one is 10? Then this one is what's that? 40. Oh no, sorry. If this one is 10, then what should I do? This one is 10, this is 500, 510. How to get a square root 500? How am I going to find how to find a transmission line square root of 500, which is equal to 20 something? How? Where to find? But okay, if you do physical transmission line, it's not. But you will do circuit design. You do circuit design. You know circuit design. You know a strip line. Do you know? Have you seen a microstrip line before? Microstrip circuit design is actually the same as your PCB board. Okay, your PC board is the same. So that means you have a conducting plane below, you have a strip below in front. So you see your circuit board, you can see so many lines, right? You can see all these things, right? Okay, this is what we call a microstrip line. Now, the impedance, the characteristic, this is a transmission line also. Okay, this is a transmission. Right from the beginning, we introduced this is a kind of transmission line. Now, the characteristic of impedance of the transmission line of this kind, okay, is proportional to the thickness of the substrate h over width. This is the width of the substrate. Okay, that means, you see, normally you also depending on epsilon r of the substrate. Alright, but basically if you use a certain kind of a substrate, h is fixed, epsilon r is fixed. That means that characteristic impedance is inversely proportional to 1 over W. Okay, so that means you can design by controlling the width of the thing. Alright, so if the width of the 50 ohm line is that thick, 50 ohm line is that width of a 50 ohm line is that wide, that wide. This is the width, okay, this is the width. Alright, if this is 50 ohm, so if need a 20 ohm, right? No problem. Okay, I use a transmission line like this, then I connect to the load here. This is 20 ohm. Lambda by 4. Like that I can do my matching. I can have a 8 ohm connect to a 50 ohm and without any refraction coefficient, without any standing wave in the circuit. So anything below, anything forwards, okay, anything forwards, there will be no reflections, and no reflections and no standing wave. No standing wave is always good for a circuit. Alright, so this is another important result that you can actually use to do matching. Alright, finally, if the length of the transmission line is lambda by 2, that means the input impedance is the same as exactly XL. If you connect a half wavelength of transmission line, the input impedance is exactly the same as the load impedance. Alright, if you substitute L is equal to lambda by 2 over there. Alright, are you okay, everybody? Is it alright? Now, example, the open circuit and short circuit impedances measured at the input terminal of a lossless transmission line of length 1.5 meter. Okay, if given as 1.5 meter, alright, 1.5 meter, that means you need to find L. You need to find lambda. Okay, you need to find lambda, but it's not given. Okay, but never mind. Okay, you are asked to find K. Okay, that means you have to find the lambda yourself, right? Because K is equal to 2 pi over lambda. Now, you are given open circuit impedance and short circuit impedance. Now, what is open circuit impedance and short circuit impedance? The open circuit impedance is these equations. The open circuit impedance is this equation. Z open circuit is equal to this. Short circuit impedance is equal to this, and open circuit impedance is equal to this. You see that the two equations have two unknown, Z0 and K. Okay, the two equations have two unknowns, Z0 and K. So you are given input impedance for open circuit and input impedance for short circuit. Okay, and L is equal to 1.5 meter. You can see that you put the two equations here. Only two unknown, Z0 and K. So you can actually solve for Z0 and solve for K. So Z0 is equal to square root of Z in OC, Z in SC is equal to 75 ohm, and K equal to 1 over L up 10, which is equal to 0.3628 radians per meter, or lambda is equal to 10 meter. Alright, so make sure that you know the equations well. Alright. Now you are asked to find, without changing the operating frequency, find the input impedance of a short-circuited line that is twice the given length. Input impedance of the short-circuit line, what is twice the impedance length? So if you just use the same old equations over here, same equations over here. Now L, instead of 1.5 meter, you put L equal to 3 meter. Since K you already know, you just find Z in SC. And what is the last one? How long should the short-circuited line be in order for it to appear as an open circuit? Short circuit appear in open circuit. Short circuit appear in open circuit. Very simple. Short circuit is zero impedance. Once appear in open circuit, become an infinite impedance. Of course, the length is lambda by 4. Okay, so of course its length is lambda by 4. You can sub in the equations, or basically, you can get the answer straight away. Now, ladies and gentlemen, any questions? I will just do a recap. Okay, I will do a recap because it is worthwhile, more worthwhile to do a recap than But I hate this thing. Why is it so slow? Alright. For a transmission line, okay, you have exactly the same characteristics between the plane wave propagations and the transmission line. Okay. Now, in general, a transmission line will have a propagation constant gamma is equal to alpha plus j beta. Alright, but in your syllables, okay, your transmission line will be lossless transmission line. Okay, it will be lossless transmission line. Therefore, gamma will be equal to j beta or jk. Okay, you only deal with lossless issue. Now, when you deal with lossless issue, when the Z0, okay, which is equal when the full formula of Z0 is like this, lossless, R will be equal to 0, G will be equal to 0. Therefore, Z0 is equal to square root of LC, and gamma will be equal to what? Omega times LC. Okay, gamma now is equal to J beta is equal to J omega square root of LC. You see the same similarity once again. Alright, gamma equal to J beta equal to square root of LC. And this one, remember this side here, your K is equal to omega mu epsilon. Look at the similarity. Look at the similarity here. Omega square root of mu epsilon, omega LC. R equal to 0, G equal to 0, J and omega brings out. Okay, so gamma equal to J beta equal to J omega square root of LC. K equal to omega square root of mu epsilon. look at the similarity. Alright, so we deal with only lossless transmission line. Alright, lossless transmission line for you. And with the lossless transmission line, okay, we can do calculations, we do analysis of lossless transmission line by using this simple model over here. The most important equations, okay, is your transmission line equations, which is equal to Zi equal to Z naught ZL plus JZ naught tangent KL ZL plus J Z naught plus JZL tangent KL. Okay, this is your most important equations that you need to definitely to know. And with that equation, what we normally do is to translate this this ZL into a ZI over here. Translate the ZL into a ZI over here. And with this ZI and VG and ZG, I can find VI and II. Okay, I can find VI and II because this is a simple Thevenin equivalent circuit. Now, with VI and II known, there are several things I can find. I can find the power supplied by VG because it is equal to half VG II. I can also find the power absorbed by ZG because it is equal to VG minus VI, which is equal to VZG times ZI. Okay, I can also find the power go into the transmission line, which is equal to VI II conjugate. Alright, so I can, with the Thevenin circuit, I can find VI II, so I can find all the three power. And the power that go into the transmission line will be the same power absorbed by the load because the transmission line is lossless. Okay, it cannot go anywhere but be absorbed by the load. And then also with the VI and II, we have derived equations to relate VI and II to VL and ZL. Okay, VL and ZL. Now, you don't have to find VL and ZL by using equations. Okay, look at which one is more convenient because VL, IL, and ZL are related. So you need only to find, for example, you find IL, then VL is equal to IL times ZL. Or you find VL, okay, then IL is equal to VL over ZL. Alright? So just do any one of them. Okay. Now, then after you know VL and IL, okay, or VL or IL, then you can use another set of equations to translate to the voltage and current at any point along the transmission line. Any point along the transmission line. Same thing when you have the gamma L here, the gamma L at any point along the transmission line will have the same amplitude but propagating at twice the speed. Okay, e to the power minus 2jk L. Alright, so basically this is in a nutshell what we do. Okay, so you see these are the two equations over here, which is repeated the slide. Which is repeated here, never mind. Okay, okay, this is the transmission line equation that we need to know. Okay, this gamma L, which is the refraction coefficient at the load, which is bear the same similarity, theta 2 minus theta 1, theta 2 plus theta 1 is the same, so that one you got no issue. Alright, and the gamma along the transmission line is propagating at twice the speed in that sense. Okay, and you can find the refraction coefficient at anywhere along the transmission line by using Zi minus Z0 or Zi plus Z0, which is the same as finding from here. Okay, so once again, these are the two equations that you need to know. Now, and these are the two equations that you need to know which link, the current, at the load end to the voltage and current at any point along the transmission line. So you can have VI, you can calculate IL, or you can have II, you also can calculate IL. All right. Sorry, this I do not know why it's so slow. Displaying a page. Everybody. While we are waiting for these slides to change, any questions? Any questions? 51. Sure. This guy just doesn't want to move. Hey, come on. Oh, this is the one. Okay, the one causing the problem. Okay, the maximum and minimum. The maximum and minimum, once again, alright, make sure that you have these equations. Maximum, minimum for voltage and maximum, minimum of currents. Alright, you need the maximum, minimum for voltage and current. That one is being asked very, very frequently as well. Okay, power flow, remember, is half real VI conjugate. That one is okay. 51. Okay, what is the issue? Huh? Alright, basically what is being said is that according to the transmission line equations, if the length of transmission line is equal to a quarter of the wavelength, the input impedance is equal to Z0 squared over ZL. Okay, the input impedance is equal to Z0 squared over ZL. Okay, that means you can use that particular formula. Okay, use that particular, this is an important formula, Z equal to Z0 squared over ZL. Use that particular formula to provide a certain matching. Okay, let's say I have a circuit which characteristic impedance is equal to 50. And I need to connect it to a 8 ohm transmission, 8 ohm load. Now, if I connect an 8 ohm load directly to a 50 ohm transmission line, there will be a reflection coefficient, right? And if a reflection coefficient, there will be standing wave along this transmission line affecting the circuit upstream. Okay, so there will be a standing wave from here and affecting the circuit upstream. So what I can do is that, okay, if I put a certain transmission line in between the 8 ohm load to the 50 ohm transmission line, can I get an input impedance here? Z in is equal to 50. If I get an input impedance here, Z in is equal to 50, that means this transmission line will see a 50 ohm load. And if see a 15 ohm load, there will be no standing wave. Okay, so how am I make sure that this input impedance here become 50? Now, according to these equations over here, Zin is equal to Z0 squared over ZL. So if my Zin need to be 50, what is my Z0? What is this value of Z0 here needed? Will be Z0 squared over 8. So I can find what is the Z0 needed for this transmission line. So if this Z0, that means Z0 squared is equal to 8 times 50 is equal to 400. So Z0 is equal to square root of 400 is equal to 20. So that means if I insert a 20 ohm characteristic impedance transmission line between this and this, okay, and make it a quarter wave length, that means the input impedance at this point here will appear as 50, and now this is matched. There will be some standing wave from here, obviously, because you see at this point here, delta is equal to 8 minus 20 over 8 plus 20. So there is a standing wave, but the standing wave limited between these sections only. Within this small section, and will not disturb anything upstream. So that is one way able to do matching. Alright? And of course, if you using physical line, you can't do it because sometimes the Z0 that you require come out to be a very fancy number, 26.5 ohm. How to do that? But 26.5 ohm is no issues when you do straight line because you can actually design by controlling the width of the straight line. Because the width of the straight line, when you control, you know, when the thick edging or lithography, laser trimming, you can control it down to 1 micrometer. So what is 23? What is a few millimeter that in anything? So no issue. Okay. So when we do circuit design, we can use this method to control the impedance matching. All right. The next one is not that significant. It's trying to say is that the same impedance will appear every half a wavelength away. Okay, the same impedance will appear half a wavelength. So you connect a half a wavelength line, you still get the same impedance. Alright? Okay, any other questions? Any other questions? Any questions, ladies and gentlemen? Alright, what we are going to do Friday, once again, okay, Friday we will finish the last tutorial 8, right? We will do tutorial 8, and after tutorial 8, we will do the CA2 for the last couple of years, okay? See, as much as we can, we will do the CA2 for the last couple of years. And anything left over will be bring forwards to Saturday. Okay, we'll finish all the CA2 and we'll do the last 3 years of exam paper on the propagation and all these things back. Now another thing is that okay, for those who were late, okay, CA2s cover only chapters. Where is the S missing? Cover chapters 4, 5, 6, and 7. Okay, chapter 8 Smith chart will not be covered, and chapter 8 will be excluded from the CA2 as well as exam because all of us felt that we don't have time to do it. We don't have time to do it because basically CA1 eat into our lectures time. Alright, so we will not be including chapter 8. Alright, and next week, okay, next week Tuesday, please be punctual at least 10 minutes before you arrive at EA, at least 10 minutes before, because we will probably let you in 5 or 10 minutes before, get seated, and then we will do CA2 exactly at 2:30, alright, 2:30 to 3:30. And then next Friday, we will review that particular CA2. Okay, we will review that particular CA2. We'll show you how to solve that. Okay, we will show you how to solve CA2, and then we will do a final revisions next Friday. Okay, and from there, I will do office hour after the training weeks. All right. Any questions, ladies and gentlemen? All right. If not, well, I will see you on Friday. Okay. Thank you.